Yeah, I'm Lars. I'm working for SAP Hybris in the Hybris Labs team. My job is to take SAP software and build new technologies around it. And yeah, building prototypes. So no customer, only fun on this way. So yeah, and then you have to find a hobby, and that's more is this Minecraft, playing lots of Minecraft. But at one point you want to get a little bit serious and also bring this maybe back into the office. So I combine this now with reinforcement learning. And that's the reason I'm here. So what problem do we want to solve today? Oh, by the way, who never played Minecraft? Oh, yeah. Yeah, good. Okay. There's always someone who didn't play Minecraft. So, yeah, we have this image here. And there's somewhere a robot, and he has no idea what to do. So, no idea what this blue block means. Also, I think even people who don't play Minecraft will recognize this red, yellow, orange stuff looks not so good. So this is lava. You will die when you fall in. Oh, there's also like player try to swim in lava and then you die. Right. So what's this good for? And this rock here, is it a rock? Can you walk on it? The other color, you don't know it. So the idea I want to solve is like you have a robot, has no idea what's going on, where to go. Yeah, even don't, yeah. What the blue block is meaning or something. Yes. So no PO, no Scrum, nothing. He has to do it by its own. Okay, and therefore I'm using Minecraft. It was invented by Marcus Notch Persson, Swedish guy. 2011, first version came out. He founded Mojang, the company. But at one point he was a little bit bored and wrote on Twitter, I want to get rid of it. Who was buying Minecraft? And Microsoft bought it for, I don't know, 2.5, 2.7 billion, something like this. First thing what he did was buying a house in Beverly Hills and rebuild it in Minecraft. So, yeah. It was only 70 million, so he have enough money left over. Yeah, it's one of the best-selling PC games all over time. The idea is it's a sandbox construction game, so it's not like you're running around in a sandbox, it's an open world, so you have no rules like you have to find this or that, you can do it by yourself. Its creative building aspects are inside of it, and yeah, three-dimensional environment. So with this building thing is like you explore the world, you find some resources, yeah, like wood. With wood you build an axe, get more wood, find stone, and so on. This is the crafting aspect, and from time to time, especially during the night, some zombies, skeletons, or creepers like this one comes by, and you have to fight for them, against them. So that's the idea of Minecraft. With this, you couldn't really solve some reinforcement learning or so. So therefore, is the project Malmo. It's from Microsoft Research Lab, an open source project. You can download it on GitHub. I think it was invented somewhere here in the UK, but there's also some people in Seattle. Someone on LinkedIn follows me, he's living in Seattle. So, and yeah, it's based on Minecraft. And therefore they're using also Minecraft Forge, it's a modding framework. Modding stands for modification, so I learned when you come up with these words like you're using creepers and all this stuff. Kids know this, modding they know, but it's modification, Minecraft Forge. So what they are doing is like download the Java package from Minecraft, disassembles everything and hooks in some points where you can control the agent, control the environment itself, also the behavior of some blocks, also get information out of the game, and so on. And yeah, from Project Malmo, they did it for reinforcement, or for AI especially. Therefore, you have a mission XML file, so they're using XML, no JSON, no YAML or something, XML, where you describe your scenario, all the blocks, and also the rewards. I will get later on this. You get a world state out of this, so you know where you are, what's next to you. You can also get the images of the scenarios, and it's important to send commands to the agent, so you can move. The agents itself are written, you can write it in Python, so all the tutorials, most of them are written, available for Python. There's also Lua available. This is because of Torch, which is also machine learning framework based on Lua. C++, that's the reason also the framework itself, Malmo, the modding stuff, the backend was, or the back part of it was written in C++, so they only have wrappers around it. C#, yeah, it's Microsoft. No one else uses C# really. And Java is also there because Minecraft itself is written in Java project, or Minecraft Forge is a Java framework normally. And the arcade learning environment, this is something like OpenGym, where you have some different Atari games also. There's also, for Linux, this is available. Okay, and yeah, there's a paper about it, and something about robotics, computer vision, planning, and so on, and also reinforcement learning. So the question is, what is reinforcement learning? First of all, we have supervised learning. This is the thing with cats and dogs, where you classify everything, and then you show a picture of a panda bear and get back maybe cat or dog, depends on. Other part is unsupervised learning. So you have unstructured data and you try to find some similarities into the data. So something goes up, something goes down, there's maybe correlation. This is unsupervised learning. And then we have a third part, and this is reinforcement learning. So this is something different than images or data structures. Reinforcement learning. And at reinforcement learning, we start with an agent and an environment. This could be a world, Minecraft world, some other world, some environment. And the agent sends an action to this environment, gets back an observation, and the most important part is the reward. So based on the reward, the agent can learn if this was a good move. So it starts with one state, moves to the other state, and gets a reward back. Depending on if the agent dies with the next step or the game finishes or something like this, it was a good move or a bad move. So read starts again and try to learn based on this state, the movement, the next step. I have later on an example for this, but this is the basic idea of reinforcement learning. And from David Silver, he is from DeepMind, which Google bought, and they also did AlphaGo and AlphaZero stuff and all the Atari games. There's also some tutorials available on YouTube where he explains reinforcement learning, and this nice sentence is, it's trial and error. So I don't know if you remember when you tried to start walking, but when you see kids start to walk, they walk 2 steps, fall down, stand up again, try it again. Or maybe with bicycle, this is more, can remember this a little bit better, like you try with bicycle, if you don't hit a tree, you go further. My brother was a little bit special in this. He's just sit on a bike, drive down a hill, there was a fountain, he didn't hit the fountain, and afterwards he could drive, so there was no trial and error. But normally you have, I think, trial and error with bicycles. And there are lots of books. One of the first books about reinforcement learning is this one from Richard Sutton and Andrew Barton. You can see it's from 1998, so this is nothing which was invented last year, 2 years ago. It's old. Also the name reinforcement learning there's a paper which is older than this, but it's one of the starting books about it. And they have an example inside of it, a cliff walking example, which is available in Malmo as a tutorial, and you have a reward. So I will show it later, or next step will show it. So for each move you get -1 point. When you hit the blue field, you get 100 points, and if you hit lava, -100. And if you hit lava over the blue field, then this move is over and restarts again, and every move will be -1. So let's take a look. So here we have this. No. Yeah. Okay. I have 3 scenarios. In this one, it doesn't learn something. It's totally random moving. Here you can see it tries to find a way. Randomly it moved here now, but the chance that it will find this way is 1 by 4, because all over this block here is lava, so it falls in. So the thing, I never tried it to the end if it will ever find the blue block, maybe, but it doesn't learn something out of this, so this is useless. So therefore, I will change this to step 2. So this is the Python code for this tutorial, and I just added 3 steps, so in next step it will take the reward and try to learn on this. I saved it? I think yes. Okay. So now you can see there red dots. This is a -100, and it's getting further. So what it's now doing, it's like finding the boundaries. For each move there's also some random move. 10%, is it 10%? Yeah, it's random. The other one is taking out of the best move, try to figure out the way, and now it falls into, not so often into lava. But again, when it will find the blue one, there's no real information about to get to this path. So therefore, I'm using step 3. This is this part. I will get into the code later on. This is Q-learning. Wait, I have to change to 3, otherwise not working. Okay. Yeah. Now the same scenario, it starts to find the boundaries of the lava. And try to find the path. So at this point, it doesn't have any idea what it has to do. So the blue button, blue box field, it's totally unknown for the agent itself. It just tries to find a way here, get here some information where the lava is. There's also some number changing, but you couldn't see it really on the color change. You will see it later on when it finds the blue field. Yeah, now it runs nearly. It finds it nearly, 18, it takes 9 steps before it finds it. 9 more. And you can also see it has also no idea about falling from this side into lava, and the same field, the lava field is here. It doesn't learn that from this side it's also dying. Yeah, now it finds the blue one. Try to get there. I think now every lava field is found, right? And now it learns the way to get into the blue field. Yeah, and when it finds this way here, then now it will be easier. Now it takes, I don't know, 5 steps. Right.
Can you jump in the game?
No, it's not jumping at this. That's a good point. I didn't thought about it. Maybe jumping, yeah. But I think most of the time it will jump in lava, so... Yeah, now you can see it found the way. And with this information and with the same scenario, I can take this and it will find the same way. But this is also not so useful if you change the scenario. I will get later on this also. Okay, so this is the path it found. I think you can see the green dots. I already see them automatically, and then I thought, okay, red and green dots, there are sometimes some problems. So I just reduced every other color, and then you can see the green dots itself. And maybe you also see the difference. This one is not so bright than this one. So the color change is also some value behind it, and I will get now into this. So this is the formula out of the book for the cliffhanging scenario. Yeah, I'm not a mathematician, and it's always like fascinating to look at one of these formulas to see some arrows inside, if nice Q, T plus, also some Greek letters. It's fascinating. And then you try to understand what is this meaning, and yeah. And then I came up with this, and this is easier. I can read this. So the new Q is the value we are looking for. Arrow means, okay, we are getting this an equation mark here. So Q and S is the state, and A is the action. So I'm at one state and doing an action, moving forward, backward, left or right. Did I have it? Yeah, something like this. This is the old Q. Then we have some alpha, which calculates the complete bracket. RT plus 1 is the reward we are getting for this. So -1 for each move, blue field 100. Then we have a gamma value, which multiplies the maximum value of the new state where we currently are. I have later on an example. I will just explain the formula now. Right, and alpha is the step size. So this is how fast it will move forward. And gamma is a discount rate. So when it's 1.0, it will take the best move. When it's 0, it ignores everything it learned. So something between is a good value. I have also later on an example for this. So what I want to do now is like, I'm standing here and moving this way. So I'm finding now the blue field and how this is calculated. So this is the formula again. And we have the old Q. So old Q is this value, this from this state to this with this action. And we do it the first time, so therefore the old Q is 0. The maximum of all these movements is also 0 because we've never been there. And then we have a reward, which is 100 for the field, -1 for the move. So therefore we're getting 99. And then we have, gamma 0.8 multiply 0. So there's all these values are not so interesting. And therefore we have 99. So from this state, with this action, we are getting 99 as a value. And now, next step will be, so then this game starts again. It runs around and finds somewhere this move to this move. Formula same. Again here. This time the old Q is from this move to here. It was -1 from a previous move. The maximum Q is this here, is the 99. The reward is just -1, so we are just moving. Then we have the gamma 8.8, 99. This will be 79.2. The rest of the values are not so interesting, so I can skip this. And at the end, we have 78.2. Okay. So how does this look like in a Q table? Yeah, it's just an array with 4 values. Left, down, right, up. I took all these values, and L stands for lava because it's -101. So there will be useless information to shrink it down a little bit. So this is the first time it finds the move from this state to the left. 78.2 from up. And then it always starts again and finds the way up. So, and as you can see, the value always, it's 80% of the previous value, -1. Yeah, and in the end, this is our path. And therefore, we learned the way for this scenario would be this movement would work fine. And yeah, this is the values of 1.0 for alpha and 0.8 for gamma. I have the same thing for smaller, for half of the alpha, and 1.0 for gamma. And this is only after 40 moves. So as you can see, it's still not finished. But you can see the reward itself, it's nearly -1 of everything. And therefore the path is also totally clear where to have to move. And it's still not finished because of 0.5 of the alpha. After 60 moves, it's, yeah, you have 88. And as you can see here, it's 45. So there's some moves sometimes next to it, but the path for this is totally clear. One problem with this is like you only stay on a local minimum or maximum on this. So you wouldn't find a bigger one. So instead of a blue field, when it would have a gold field, this will be nearly impossible to find it if it's up. Okay. So now we know everything about it. So like blue field, this is where we want to go. Brown stone, fine to move. Lava, not so good. You will die. But what about the different scenario? So we have now one scenario. With this I could take it, but I don't know. I wouldn't find a train station with this scenario. This is, yeah, I will fall into lava before this. And therefore is deep reinforcement learning a good thing? So what's this? This is a mixture out of reinforcement learning and supervised learning. So instead of using cats and dogs for our image recognition, I will use the images of Minecraft itself. And this is based on a paper also from DeepMind, where they used Atari games and did also deep reinforcement learning on this. So there was some reinforcement learning for the movement itself, but they also took the images of the game. There's a YouTube video for this. we can see what's happening. Interesting, yeah. So at this point, it figured out when it shoots the ball behind the wall, it gets a better reward. Yeah, right. So what are they doing? So they have the actions for the paddle. Paddle itself can move left, right, or idle. This is something. And then they take the score itself. It's not taken out of the screen. There's some memory where the score is written in. So this is the reward based on this. And for the image, takes this image. And one problem is like, you don't know where the ball is going now. Is it going up or down? So who guessed the ball goes up? Who guessed the ball falls down? Okay, I think it's going up.
Technically, it has to be going up because no block has been hit yet. So
Yes, right, it should. But it could also start and fall down. But in the whole scenario, it doesn't matter. You want to know if the ball is in which direction the ball is moving. So therefore, they took one image and the previous image, subtract this, and then you can see a movement. And this is based for deep learning in this part. And yeah, so we can see. I think it goes up. Okay, so. What I've done was also taking this idea with the two images. So this is first scenario, then I moved to the right side and subtract these two images. This is one thing is therefore important, so I know moving from left to right, and then what will happen with the next step. So moving up, I get this information here. Moving up would work fine. Moving backward, I have no information. But also one problem is like when I'm standing in front of a blue field and moving a step or 2 steps before a blue field, doing the next step for it, I couldn't see the blue field anymore. With the subtraction, I will see there was a blue field, so the next move should be maybe going on the left side. So therefore I'm using 2 images for this. Yeah, and you can see it's a little bit confusing. Then I set up lots of scenarios for the training. So I just do reinforcement learning for each scenario. So this is our known scenario here. And this is our, just a sample out of this. And run it through the machine. And then I had 12 classifications for moving east. Bad move is when it falls into lava. Good move, nothing really happened. And super is when it finds a blue field. And this for east, north, south, west. That's missing one west, I think. Okay. And one thing is also it's upside down. So moving south means going this way. This one is west, east. So this is complicated in the first thing. I don't know. Based on Minecraft and the coordinate system where this scenario is set up. And then I took from the paper, from the Atari thing, this is the description. I can show it. Here's the paper. I have it here, yeah. Oh, can you see it? So here we have something, hidden layer with 16 8x8 with a stride of 4, and then 32 4x4. So the idea, I did this in Keras. So what I have is, a model, convolutional layer with 16 by 8 with a stride of 4, so it takes 4 out of this. I also converted the image itself to 84 by 84 in the size. Relu for activation, 32 is the other one, and then here is the 12 classes I have for the actions itself. So depending on the image and the action in the class, I can now train my model, run this through, and let's see what happens. Okay. So for the demo, I slowed down. There's a wait in this script, to show it a little bit slower. And as you can see, it doesn't find a way. So it's standing in front of the blue one. It's standing next to it also, but took a different direction. Oh, why is it dying, by the way? Okay. Let's take a look. So moving now to the left side would be a good idea, but there's no image for this. So I'm missing one more image maybe, or something like this for this scenario. So this doesn't work. But I found one or more of them which worked. So here's the code. As you can see. Was it this one? No, this way. Yeah. So this is a seed number, and based on the seed number, scenario will set up. For the reinforcement learning part, is also the random moves. For this part here, there's no random moves inside it, so I just take the images, and therefore, oh, where is it? Here. So now it moves forward, stands in front of it, moves on the side, and now it finds it. And this is done with the images itself. One more time. With this, it finds it. And I stop this one and make it a little bit bigger. So where is it with the good move? Yeah, here. So we're looking at this part here, or this part looks better. Yeah. Where are we? Here. So these are the 12 classes I'm using. So this is East bad, East good, East super. There should be East is this side left. Yeah, so this is left good. This one, then we have this two. Up is super, and right is bad. So standing next to lava is a bad thing. This is recognized by the image. Moving up is also the right move, and therefore I get the action move south, upside down, one more, and getting a reward of 88 in this case. So this is the way it's working. I can also show the demo without the weight. So it's really fast. It's not like it have to calculate something. The calculation is done on a different machine with the GPU with lots of power. Yeah. And therefore it finds the way. Especially when the block is lying on the field, then it's working fine. When it's next to the lava field, it's not so good working. So I've also found different scenarios. Okay. Questions, by the way. So if someone has questions, no problem. We can do it also at the end. Because takeaway now. Project Malmo is a platform for AI itself. You can download it. It's free. You don't need a Minecraft license for this. Don't start playing with it. It will take hours before you get out of this and getting your life back. Do some series with this. So one tip on it. Reinforcement learning. I think it's an interesting field. I'm looking also for a scenario at that company itself, how we can use this, for example, for recommendation stuff. But therefore, it's like, how do you get a bad recommendation? If the customer is never coming back, was this a bad recommendation? If, I don't know. So a good recommendation, you recommend something, he buys this, fine. Bad one is like, how do you measure this one? And if you're bored about learning cats and dogs with deep reinforcement, with deep learning stuff, I find it really interesting with what's possible with the deep reinforcement learning part. So having these two images and try to figure out a way for it. I don't know what's the problem at the moment. Why it figures out sometimes the good way, why not? But Keras has something for this where you can see which part of the image is responsible for the next move. And there's also some project, some GitHub project called Lime, where you also get you change something a little bit in the picture and get back the feedback, which part of this picture is the influence of moving left, right, or up. So this is what I want to look at. One other thing is also like, as a human, you can see there's a blue block. This is where I have to go. This is not here inside of it. So this there's an LSTM which is used for natural language processing. Maybe this could also be something useful here. What else? I'm also playing around with the hyperparameters. So with this one here. So this is just out of the paper. But I can also change this different values because I don't know how this is, the behavior of this is now working. This is made for Atari games. But maybe I have different parameters I need for this one. Because when I look at this image here, what's the influence for it? Is it this line, or is it maybe here in the back something? And therefore it's not clear which combination everything has to have. One thing more was, when I'm walking, I walk and then I fall into lava. This is not learning back. So I don't take this result immediately back for another learning process. So this would be also something like getting this information back. So instead of starting with reinforcement learning, training the data on this, just do the reinforcement learning at that moment. It learns, it falls into lava, have the picture for this, and try to learn it this way. So this is something, which is interesting. Here I have some links also. So this is Project Malmo itself. This is the book, Reinforcement Learning Introduction. It's also available online. Second version is only available online. They're writing a new version, but I think I don't know when they will release it. And there's YouTube videos from David Silver. He's doing a class where it explains reinforcement learning from the beginning with different kinds of. So I'm only showed here Q-learning, but there are different other reinforcement learning stuff available. Yeah, that's it. Yeah.
Would the image recognition still work with visual obstacles?
What do you mean with visual obstacles?
So using the images to find the goal, if you had a visual obstacle in front, if that makes sense.
So when you don't see, when you get blocked, it's also a good point. I'm not sure. At the moment, I think not. But it's also something which is like you can see the field and you can see the blue block. So building some door where you have to walk through, maybe not. At the moment, maybe because I'm on. At the moment maybe because I'm not looking for the blue block. So at the moment I'm just looking in front of me, and when there's a door, and it's trained for the door in some kind, then it could work. So this.
Just to make sure I understand, you built the training set for the deep learning with the reinforcement learning. The classification, it was done automatically. You didn't have to do it.
I used the reinforcement learning for the classification. So this is this part here. So this is the movement, is an east movement from this point to this point, and then it will go south. This means from this point going south was a good move, because here was the blue field, which now moves here or something.
So how many runs did you take to build the model? How many runs of?
How often did it? 1,000. I think I had 1,000 in it. Wait, I have the code also here. This is the code and image detection. 50 epochs, not so much. Wrong, 50, yeah. And then what I'm also doing now is like changing the parameters and then run again, and try to figure out which one was the better accuracy, and taking this one, but I realized, okay, a better one is not finding a way better or something, so this would be also like taking all new trained models and run them through the system.
Say, if you were to do this as a full-day workshop, I would attend just to sit back.
Okay, thank you.
I'm just wondering, are there any efforts where you had multiple agents and they were both learning and communicating with each other and kind of sharing their learning to accelerate?
That's good point. Malmo supports multiple agents, so this should work. I have no experience with this, but I'm sorry, I'm just thinking that now. But yeah, would be interesting part. Yeah, should work with Malmo project. Malmo itself supports multiple agents, and therefore they could learn on it. So drop one agent on this side and the other one there, and then if you take back the data in the same queue table, should work. Yeah, you're coming from a different way. It's interesting, yeah, to think about it. Yeah, thanks.
Something else, just as feedback to try. If you were to do two things, so you're currently using the single images input for the convolutional
Yep.
neural network. If you put like the previous two images in addition to that as inputs, it would give the equivalent of like a visual memory. So if that block was off to the side, you could have that be part of the input, and then have a sequence of outputs as your output that you're predicting, rather than a single output, so that you can essentially be predicting into the future. And the combination of those two things, I think, would actually solve that problem.
Yeah. Right. More images and maybe the sequence of this. Yeah. Right. So at the moment it's just like these two images and this direction but no feedback or no other data, no future in this. So therefore, I need a loop. Yeah. So it would work. First time it will. Yeah, that's what I also meant with reinforcement learning. So when it stands in next to the blue field, it moves left, right, and goes the wrong side. Doing there some reinforcement learning, say, okay, try to go this way, you don't die. Because we know these images have been before and all this stuff, yeah. Right. Oh, yeah.
Did you explore turning at all?
Turning?
Like turning the agent, so it's currently facing in one direction.
Oh.
You can play Minecraft, you can turn.
Yeah, right. This is also something, like the agent itself, it has a fixed view. So one other thing would be like to put the view directly in front of the feet. This would be something. Or also to turn around and look. This is also something more. I use this stupid robot for this in this case, but yeah, I think it will be more successful if you can turn around all 4 directions and also have what's in front of you. So at the moment you don't see what's really in front of you. There's only just one step before. Yep.
Are the agents capable of placing and destroying blocks? And have you tried running the same experiment but allowing them to, for example, like place a block down to cover the lava?
So different scenario, or
Well, it would be the same scenario, get to the blue block without falling in lava, but giving it more tools to complete the problem. So if you allowed it to, for example, you give it 50 cobblestone in your inventory and said you're allowed to place it wherever you want.
okay, this is the next step. This could be next step. So this was my first idea when I heard about Project Malmo. Like, oh, now I don't have to play. I just have to program, and then I look 2 weeks later and look what houses and everything is built and yeah. Then you realize, okay, you only can move, and to figure out how to chop down a tree to get wood. It's more than just say do it, yeah. But you're right. You can also say, okay, I have some blocks and just throw them in front of me, and so you don't have the lava problem. It is should be possible with Malmo. Yeah, I didn't try it, but you have an inventory. You can get data. Yeah.
Sorry, wouldn't that negate the use of images though? Because as soon as you put the block in, then you all the learning behind it's redundant.
Good point. Good point. Yeah, but you have to learn it with it. No. It's just thinking. Sorry.
Well, it depends if you count it as a better move, because you can put a picture where there is.
Yeah, but the next start doesn't have the same problem anymore because now you have one extra block that if you didn't back, now you have to account for.
No. For this, when you restart the scenario, you have to get rid of the blocks.
Oh, right, okay.
So this is something.
But you don't normally, right? You wouldn't on a normal scenario. Someone.
So you have to reset. Yeah. You have to reset the scenario, and then otherwise, yeah, you're right. If you fill up all the fields with blocks, then at the end there's everything would be stone, even the blue field maybe. And now you have to reset every step, and maybe because it's Minecraft, and when you take off a block out of a lava is also flowing a little bit. So this could also change the behavior of the game. I mean, if you fall into lava, it doesn't change anything. This is a simple scenario.
Is it possible to play with a bot, for example, to train them and they can to have an army of bots that can get resources for you and you just the consumer or just use them?
Okay, yeah. Yeah, this is homework, yeah. But I'm not sure you can control it. I don't know if you have the feedback from Malmo to say, okay, what action you are doing at the moment. But this is a good point. I tried. Oh, it's a good point, yeah. Just to learn it by training. Yep.
Is there any memory involved here? So I'm quite easy to imagine the system getting into a loop where you've got a complicated map, you just sort of like moving around in a circle forever. Imagine like you've got different paths you can take, and one path results in a square being accessible. How would you approach that?
I didn't understand it, so.
So imagine you've got like a complicated map where you've got multiple bifurcating paths, and like one of the paths you take it, you'll eventually get to the square, but it's somewhere over the sort of horizon. How would you approach that sort of?
So, for example, when the yellow block would be up of the blue block.
Yeah, or maybe like you think about the lava, maybe there's
Yeah,
forms.
this is with the alpha and gamma stuff. You can try to force it a little bit slower movement and try to find a better way. So instead of a local minimum maximum, you get a global one. Is this answering your question? Yeah. Time is up. I'm around here, so, but I have to leave to the airport at, I don't know, 3 o'clock or something, but I'm still around here. So.